All right, so my name is Mike Connaughton. I'm with Nexans Data Center Solutions. And what we're going to talk about here is physical layer optimization. It's actually pertinent to a few of the discussions I've heard because a very popular issue going on right now, I'll call it, is the MSA. The positives about MSAs is they get delivered quickly. You get new PMDs that come out. The downside of MSAs is now you have 100 options and you're not really sure which one is the best. They all have use cases, but if you aren't one of the target customers, you're not really sure if that PMD is good for you or not. So what we've come up with is an approach to try and help people determine which PMDs are proper candidates for their application. So just full disclosure, just a brief explanation of who we are. Nexans, very big company, $7–8 billion. We are in the cabling industry. My particular division, Data Center Solutions, was just launched last year specifically to target the hyperscale and cloud data center environment. And the products that we manufacture and sell are related to the physical layer. Enclosures, cabling, transceivers, AOCs, pathways, and such. All right. So what is the physical layer? Historically, this has been split into two from a supply chain perspective, but really physical layer is the cable and the transceiver. And we make the argument that the transceiver performance has more to do with the cable and vice versa than either of them have to do with the host that it's plugged into, whether that's a switch or a server. And if we're looking at optimizing performance, you really have to look at that entire piece. So we're showing on the slide here, okay, I am up there. Just as an example, we're showing the MSA spec of 100G CWDM4. And the Intel gentleman a few minutes ago was talking about the different penalties that are associated. He was talking about CWDM8, but in CWDM4, there's don't knock over with water. Losses associated with the cable, with connectivity, interference, and dispersion penalties. All right, so that totals up to your 10 dBs, 2, 4, 5, 8 dBs. But in there's a channel insertion loss of 5. That channel insertion loss essentially is the cabling. Now, a couple of issues can happen in real life. You might have existing cabling that has higher than 2 dBs of loss. Can you use that? Do you have to replace that cabling? Or, kind of where a lot of these MSAs came from, what if I had a lower performing transceiver, but I had a better performing cabling? Can I make those trade-offs? The short answer is yes, you can. You can start trading some of these penalties. If you have some with better performance and some with worse performance, as long as it balances out, it will still work. Essentially, the point we're making on this is that you want to analyze the performance of the link, not just the components. All right? In standards, we specify them as components for a lot of good reasons, but as you start scaling, that can become a limiting factor. So when you start looking at the analysis, if you looked at just the cabling, and we want to compare, as an example, 200G options, and we're going to compare CWDM4 and PSM4. You could pick any two, you could pick 10 that you want to do. But for illustration purposes, we picked these two. And from a cabling perspective, the big difference is, with CWDM4, you're using 2 fibers with LC connectivity. When you're using PSM4, you're using 8 fibers with MPO connectivity. More fibers, more expensive connectors, therefore it's more expensive. So in a silo, if you were looking at this, it seems clear they would use duplex LC. Significantly less expensive, 3 to 4 times less expensive. If you look just at the optics, here, what issues drive some of those costs? You're dealing with parallel optics versus wavelength division multiplexing. There can be encoding schemes that are put in there. There's also market adoption. So how available, what's the volume associated with that particular product? All of these things drive those price decisions. When we look at the data in the recent past, it would say that PSM4 about 1.5 to 2 times less expensive than CWDM4. So if you looked at this by itself, you would say PSM4 is the clear choice. Well, those two pieces of data are at odds with each other. So what you really need to do is look at the total piece. So when you add those two things together, and you have to make some assumptions here, and some of the assumptions we have in here is, well, how long is that run? How far apart are these two transceivers from each other? Every data center design is going to be different. But in this example, we see that PSM4, 1 to 1.5 times more expensive. All right, so it tells you from this example, when you capture the data in this format, that CWDM4 is less expensive. And this tends to drive, when we look at the popularity, this is part of the reason we see CWDM4 as being more popular. This doesn't answer all the questions. There can be reasons why somebody would want to use PSM4 anyways. Breakout capability would be a prime example. But the thing that we drive towards is the fact that you can relate now this cabling cost, which kind of historically was viewed as data rate agnostic, but now we can take that physical layer and start equating it into dollars per gigabit, the same way you look at everything else. Now, the way we arrived at that is, essentially, in some ways, it's a simple tool. Right? We just go out and get the costs of these various devices, and it's a tool that we've developed and we've used with our customers over the years to help drive this message, look at the whole link instead of just the individual components. But step one of the tool is determine, will it work? If you have an existing cable plant and you're interested in CWDM8, step one, is it going to work? Is my insertion loss acceptable for that technology? If the answer is no, doesn't matter what it costs. Eliminate it. But then you can start looking at other options, take all the ones that work, compare them, and see which one is least expensive. Doesn't mean that you're automatically doing or using that technology, but it gives you an important piece of data to do that. So the conclusion we draw from this, it's more than just cable, it's more than just optics. Physical layer is the physical layer. You have to look at that combination of the two. And what we're suggesting to the community is that we can take that tool that we've created and used for ourselves and for our customers and make that available for everybody's use. The inputs would be essentially the physical layer criteria, so we'd be able to determine what's needed to make these various products work. And then you would have cost input that people would put in independently, and it would give them that comparison that they need. And to me, just listening over between last week and this week, between OFC and OCP, all the MSAs that are coming out, I'm a firm believer that options are a good thing. More options are good, because that means there's something out there that's most beneficial for you, but it can be confusing. And one of the key uses of this tool can be a way to filter out of the 15 available 100G or 400G options, which one should I consider? It could limit you to 2 or 3 options, and then you could go through some other analysis around port densities or power densities or something else to drive that decision. And that's what I have. Any questions?
Questions? So first question's for Mike.
Okay.
Anyone? Okay. Yeah, go ahead.
So you mentioned that you might make this tool available. Is a version of it available now?
We have a version available that I wouldn't, it's for our own use. The guts of it, where it actually is most powerful, is in the multimode arena, because there's a lot of variables that have to do with the transmission penalty. But we have a version that we would start with, that we would think would be the straw man to begin with. So it has all of the, essentially, math that goes behind it. And then I think what the community would do is decide what inputs go in, what outputs are desired, and then make the interface.
Thanks.
Okay. So Scott, come on up. If someone could, so this is open discussion, but I want to bring the speakers up again. If someone could go out, Chris, can you go see if you can find the Facebook guys right outside the door? And tell them to get back in here? And NTT. Right, okay, there you are. So open discussion, you're part of this session because you care about optics. Questions? Help me out here. This is the part I was most worried about.
The carrying crowd is getting less.
Please, somebody. Oh, I've got another. There should be 2 microphones. 1, 2, good. All I need is questions.
So on the stuff that you were talking about,
Yep.
when you were talking about looking at the transceivers to predict them failing, how are you getting that data? Are you logging into each individual switch, then logging into the port, then grabbing the EPROMs individually, or are you doing something SNMTP wise, or?
The original, actually, we found this kind of a thing is very interesting. We using switch to reading all the DOM information. Originally, we try to use this one to control our data center's environment. You know, the Facebook data center is different than any other data center. We don't have AC. We use lateral cooling. So in some of the area, we saw the problem on we call the dead corner, which is the temperature going to the roof. We don't know exactly what happened. So originally we tried to use this one to monitoring the temperature. Okay, and then suddenly we found some of the transceiver actually failed. Then we look at the data, and then so we try to compare with the temperature versus how it fell. And that is actually gave us some correlations we studied. So in short, yes, we use the switch to record all the data. We pull the data. You can decide whether every minute you want to pull this DOM information from switch from every port, or you can decide 10 minutes, and then we have accumulated tons of the data in our data center.
And then you just put it in some kind of time series database and then compare it?
Yes.
And then have y'all decided, or are you going to branch out and so then start taking that data, then mapping it over workloads and weather and all that other stuff?
Yeah, for the working load, because we don't have any actually the monitoring for our purpose, we don't have any actually monitoring on the traffic load. So what do we perform? As soon as this kind of the indication we believe is going to fail. So what we did is that we pull those units running in the lab, and then to give a full loaded of the traffic, and then to accelerate the failures. That is what we have to see.
So just to add on to that, you said you pulled 20 out and killed them.
Yes.
Did you try pulling 20 that didn't look like they were bad out and see what happened to them?
Yeah, we actually pull more, and then some of this unit, if they don't see this slope going down, we don't see the failure.
Okay, just do basic science.
So this is basically, yeah.
Anybody else?
To follow up on that. So Vincent, the app you're looking for is just an open source OOM-based version of that app that looks at the slope and predicts a failure.
Yes, I think the way we try to do is that we don't, want to this information is kind of varies between the. We don't want to have this information depend on the switch. We want to have this information recorded on each unit. That is what we do. Yeah.
Each optical.
Each optical, yeah. So basically, we're looking at the EEPROM, like you mentioned. Mm-hmm. We open a lot of address that will allow us to record those information.
So you want to write the information yourself?
Yes. Yeah.
Oh, cool. So it's available.
So available, yeah. So whenever you pull this optics, those information will be available. You plug into another switch, it could be the information there. But right now, we try to doing some like a script from switch level to calculate it where the slope is meet the spec or below the beyond the stress threshold, and then which we can see this is going to be fail. So something like a failure indicator, something like that.
So there's a monitor running on the switch.
Yes.
It's writing data into the EEPROM.
EEPROM.
So if you pull that and put it someplace else, it's still there.
Yes, it's still there.
Oh, that's all doable. Yeah.
So Don, not to put you on the spot, but this is something we can help with, right?
Yeah, they're going to want to write the app because it's on their switch. we can certainly help discuss, we, Finisar, can certainly discuss what that algorithm should look like and where those thresholds are, although it probably depends on which optic vendor.
Yes. So that is actually right now we're working with some of our partners to build in the real devices, and then we try to write some script on our switches, and then so we.
Almost all the MSAs have 128 bytes reserved for the vendor to write into.
Right.
Yes, exactly. Yes.
Is that what you're intending?
Yes, yes, yeah. The problem is that, for instance, like you see this slope, right? This is where we really focus on. How many data points you want to have to calculate the correct? So that is the problem we have it.
You have 128 bytes.
If I can ask a question, one of my questions was going to be, how much history do you think you can build? I mean,
Yes, that is.
Writing over history.
Yeah, I think the way we try to record it in the first time it's power on, we try to record it. That is definitely we're going to. And then whether we want to have the second one is continue to write overwriting, and then we can have a switch to calculate whether they build in certain slope. That is the point we're going to record it, and then they will open the third point that will record it if this is continuous. So this is some like initial idea we try to build in this algorithm out.
So let me follow up on Vipul's question with this. let's work on this together.
Which one you want?
Yeah, let's work on this together.
Okay, yes, yes.
So what are the failures apart from the laser?
What, sorry, what's it?
What are the other failures apart from the laser?
So if you look at our analysis, I think a majority or the 98% of the failure is from laser. And so on this moment, we don't want to focus on any other failure mode. We only focus on the laser. So in our earlier talk, we're talking about working with our partner to squeeze to give a more screening or stressful screening on the laser side. That help. But from the service perspective, you want to, after you finish all this screening process, you make sure that your product is have a, like in the bus stop in the bottom is a flat, high quality, but they still have return some of the failure, which can cause this problem. So that is why we can build in this mechanism to predict the failure, even after the screening process implemented. Yeah, actually the majority of the laser, if we address the laser very well or screening pretty well, right now we can see actually the CWDM4, the performance actually is pretty good. But because of the laser failure, it's causing more problem for us.
So are these from single vendor or from the multiple vendors?
Multiple vendor. So I think this, so that is why based on our understanding, and I think this is like the industry's problem on the DFB laser fabrication, the process. And then someone said it's assembling can cause a problem. Yes, assembly can cause some problem, but I think the biggest problem actually coming from the wafer level.
Do you see the errors in batches that you're buying from, or are they more across the board?
Yes, it's from certain batches, yeah. And then when you're talking about the batches, and then there's more details to talking, right? For instance, how this the batch of the wafer, how they using criteria to on the wafer level management, level. And I don't think it's currently for the India phosphide laser, there's no standard like the industrial standard to code the wafer level of the yield management per se. Because I've been working on the carrier tanker before, so we know how to doing the CMOS management, yield management, step by step. I don't think the India phosphide never have any experiences or the practice.
Yeah, so you guys are living the dream now. But yesterday we saw they're going to do big modules that plug into multi-chip modules with fiber coming out the top.
Yeah. Well, that is we call it the Copackaging.
Yes.
So yeah, this is a Copackaging. We want to do that.
Okay.
Yeah.
Because then that'll, well, they actually had an off-board laser in their example, but I know sometimes you can integrate that too. So.
Yes, it's yeah. I don't think it's going to be like going to happen within 1 year. It's going to be a lot of challenges, like IEO interface standards, and then how to integrate it. You know, a lot of the issues. Yeah. Yeah.
Just out of curiosity, what is your failure rate on CWDM4 pluggables?
I'm afraid I don't know, or I cannot tell. But you know, for last year when we're talking about the Facebook's, you know, the optical supplier qualification process, and then I basically what I have been working with a multiple supplier. We ask them to deliver their predicted feed numbers or predicted MTBF, mean time between failure. That is actually give us like the annual failure rate if you calculate it well. And then those predicted number is based on your component level as well as your packaging confidence. And then so right now, if all the suppliers meeting that one, we're okay. And then roughly number, if a guided is annual failure rate, it should be less than 1.5%. And that is corresponds to the mean time between failure is about 600,000 hours.
That's what we're seeing at the 40 gig side too.
Yeah, 40 gig.
Yeah, that's what when we switched around the same time.
Mm-hmm.
That's the same. It seems to be pretty rock solid.
Yeah.
600K, that's how many feet?
That's, if I remember correctly, that number is about 800 or 1,000 level, yeah. Because the feed rate is very challenging to calculate it. Its feed rate is depends on your power on hours, which is like you ship it out and the customer can waiting for, I don't know how long to power it on, right? So that is number is actually is not very accurate.
Fairly generous value. It's not a very tight fit.
Oh yes. So as I mentioned, if we take this laser out, this feed rate could be double digit.
Okay, 400G. Anybody got any 400G questions?
I don't need
No. What else? Anybody? Anything?
I'll ask a question about 400G. What's going to happen to 200G?
That's another crystal ball question.
I mean, I'll tell you from my perspective, kind of looking at it, there's the big guys, the hyperscalers, that kind of won't need 200G. They already need 400G, so 200 will almost not exist. And for the enterprise size guys, smaller enterprise size, 200 is too far away to make a business case for it. And by the time they need it, it may not exist. That's, again, my thought process. I'm just wondering.
It's plausible.
Opinions out of the room?
No.
Okay.
Yeah, I agree with no.
No.
We don't want to repeat the 4100.
Don't do it.
Yeah,
We don't want to
200.
we don't want to repeat the 4100.
Yeah.
And the double density thing, the double den, stacking the QSFP, that doesn't make sense either.
Okay. More? Others?
I guess the corresponding question is how long can you wait for 400G?
I can wait a long time. I'm in financials. Just for 401K, I don't care. But no, it's now we're just now fully, well, not almost fully 40. So for us to jump to 100, I mean, the only reason we would do it is because a switch manufacturer would say, we want to sell you the switches for cheap. We don't have a reason for it. And then that's when that migration is done was because it's it's a huge disruptor. I mean, we can't ever go down. We're never going to be down because we don't want to lose your money. So it takes forever for us to switch over.
That's one of the examples where we think the tool comes into play, because if you start relating cabling and all these back to dollars per gigabit, you can actually do a lot of math that says the most economical way to do things is with 10 gig connections, as opposed to 100 or I mean 400 might start pushing it the other way. But you have a density penalty when you're dealing with that. So if somebody doesn't actually need 400, but they're at 100, they could kind of use the tool and say, am I better off just keeping aggregating 100G links, or is now the time that I would flip over to 400?
From a service provider perspective, because that's what I work for, what we saw going from 10 to 100 is when the actual flows went to over 100 gigs. And then we saw the uptick of, or over 10 gigs. And then we saw, okay, how long can that last? And then we are now seeing the jump to 100 from all of our customers.
You're seeing what?
The jump to 100 gigs from all of our customers. So now 10 gig is a low-speed aggregation device for us. And we can live off of multiple 100 gig bundles for quite some time until we start seeing over 100 gig flows.
How will Flexi affect that dynamic?
That's to be determined. I'm not quite sure. So.
Because it's possible that it just allows you to work with
Yeah, I mean, there's a lot of things that we can do for flows in terms of hashing.
Right.
So, I mean, as long as we can hash correct, as long as we can get good hashing out of the boxes, it's not a big deal. I mean, at 10 gig, we saw 12 10 gig circuits being bundled up together, and that made sense for a lot of customers. Not for us. We usually saw about 8, and then we made the jump to 100.
Okay, anybody else? More questions? Okay, you got 10 minutes to get back to the floor and look at the OOM demo in the Sonic booth. Thank you all very much. Appreciate your help.